All right, today what I'd like to do is I'd like to do the same kind of example we looked at before break, but in the context of using something called the continuous convolution formula, which actually, I mean, the formula itself is difficult to understand, but using it, it's not too hard. And it does simplify the calculation quite a bit. You'll see here. I'll illustrate for you here. So let's think about it in general. We're looking at something called the continuous convolution formula. For what? Well, in a special case, for finding the PDF probability density function of the sum of two non-negative continuous random variables. Continuous convolution formula for finding the PDF of the sum of two independent, they do need to be independent, continuous random variables that are also non-negative. I'll say continuous non-negative random variables based on the PDFs of those two continuous non-negative random variables. Continuous convolution formula in this special kind of setting. So let's say we've got two independent random variables, X and Y. They're independent. With PDFs little f sub X of little x and little f sub Y of little y. Okay, as we've often done, we'll call the sum of these two random variables W. It's, maybe it'd make more sense to call it S, but I've been calling it W. Let W equal X plus Y. Question is, what is the PDF of W? Let's derive this in the abstract. Okay, and then we'll apply it to a certain situation. In fact, the same situation we looked at before spring break. We'll use the CDF method. Start with the CDF method. Cumulative distribution function method, where we first write down the CDF of W, and then we differentiate it to find the PDF. Right, as we've done a lot. So capital W is my random variable that is the sum of capital X and capital Y, and it's this letter little w is the variable for the CDF and PDF of capital W. As always, remember this is always true whether your random variable is continuous, discrete, or mixed. The CDF is the probability that the random variable is less than or equal to the given input for this function, little w, as always. The way you compute it then after this point is what changes. Well, what is W? It's X plus Y. How are we going to do this? In general, we would have to use the joint density of X and Y, right? We need to think multivariable calculus here. Go ahead and draw a picture. Here's your plane. Label this axis X and this one Y. These are non-negative random variables, and it makes it simpler then. We can just focus on the first quadrant. What's W? W is just some non-negative number. Little w is some number greater than or equal to 0. what does it mean for x plus y to be less than or equal to little w? It means if you draw the line y equals little w minus x in this plane, it means you're on a point, you're at a point below that line. All right, this line is going to have a y-intercept of w and a slope of -1. There it is right there. The y-intercept is little w. The slope is -1. And therefore, the x-intercept is also little w. For x plus y to be less than or equal to little w means that you are below this line. And we are also in the first quadrant because x and y are non-negative. So we're in this triangle somewhere for this condition to be true. And what this means is to find this probability, you need to do a double integral over this region of the joint density. Double integral of the joint density f sub xy of little x little y. That's the joint density. I haven't said what the joint density is yet, but the independence assumption is going to help us figure that out. There's the joint density, excuse me, of the bivariate random variable xy. I'm not integrating over a rectangle here. I'm integrating over a triangle. Now, again, a few of you probably have not had multivariable calculus. It's okay. I think we can still talk about this. If it were a rectangle where x goes like from A to B and y goes from C to D or something, and if we integrate with respect to, say, y first and then x second, which is the way I usually do it, we'd let x go from A to B. The limits of integration for the outer integral would be A to B, and we'd let y go from C to D. The inner limits of integration would be C and D. But we don't have a rectangle, we've got a triangle. Here's what you do. The outer limits of integration for x in this case are still constants. For this triangle, x goes from 0 to w. W is a constant when I'm thinking about doing this calculation. When I think about doing the calculation, I'm thinking of w as a constant. After I finish the calculation, then I think of w as a variable, right? It's all in your head. It's all the perspective that you have. However, y does not go from 0 to w. What does it go from? Here's how you think about it. For any given value of x between 0 and w, I'll pretend it's right there, say, y goes from the second coordinate of this point up to the second coordinate of that point. The second coordinate of the lower point there is easy. It's just 0, right? 0. The second coordinate of this point up there depends on x. It's w minus x, in fact. This upper limit of this integral is w minus x. Okay, here's where we use independence. Independence allows us to write the joint density as the product of the regular densities of x and y individually. You could call them marginal densities. And that's a good thing. It's going to allow us to do something we wouldn't be able to do otherwise. Right? That's independence. That's the definition of independence in chapter 5. The joint density is the product of the marginal densities, and the marginal densities are the same as the ordinary PDFs of x and y individually. Okay, without making that assumption, it makes this harder. You really can't go much beyond that point. But because we can write this, here's the key. Here's one key. Double integral like this, there's really an inner integral and an outer integral. Don't always put parentheses there, but that's what's really going on. Sometimes called an iterated integral. There's a first integral, an inner one, and a second one, an outer one. For the inner one, the variable is y. I'm integrating with respect to y. Fx of x doesn't depend on y. It's constant with respect to y. Therefore, it can be factored out of the integral. The inner integral, at least, not the outer integral, like this. I'll continue using the parentheses. With respect to that inner integral, the marginal density of x is a constant. It can be factored out. Okay, is that really so helpful? It is actually, because now this inner integral can be simplified, can be in fact written without an integral sign. How? Think about it here. I'm integrating the PDF of y there. If I knew its antiderivative or an antiderivative, I could do that integral. Hey, I know an antiderivative, at least in the abstract, it's capital F. Subcapital Y. Think fundamental theorem of calculus, plug in the top limit of integration, subtract what you get when you plug in the bottom limit of integration. So that inner integral can be written without an integral sign. And in fact, it could even be simplified further. Does anybody see how? I could simplify that right there. What does that equal? What I'm pointing at. These random variables are non-negative. It's 0. Because x and y are non-negative. So they can't take on negative values with any positive probability. The CDF has a value of 0 at 0. Okay, so this is nice, I guess. Careful about writing the correct letters in all the correct spots here. That's the trickiest part. Okay, so what have we done? We've shown that we can write the CDF of capital W, which is x plus y, as a single integral, not a double integral, of this product. What am I after? I'm after the PDF of W. I need to differentiate this. Little f subcapital W is the derivative of capital F. In other words, I need to differentiate this integral. That sounds kind of familiar, or it should at least. Where the variable is in the upper limit of the integral, that sounds like a fundamental theorem of calculus, part 2 problem, right? Except there's a fly in the ointment here. That's not the only place W appears. It also appears right there. So what does that mean? That means we can't use the fundamental theorem of calculus to do this derivative. However, there is another rule that we can use. You probably never heard of it before. In fact, it's not something that I think about much. It's called Leibniz's rule, Leibniz integral rule. You could say it's a generalization of the fundamental theorem of calculus. It tells you how to find the derivative with respect to x of an integral like this, where x appears here, here, and here. which is essentially what the situation we're in, except with a W instead of an X. The T here is playing the role that the X does for us. I want to compare these things here. Compare this with this. For our problem in purple up here, W is playing the role of X down here, and X up here is playing the role of T down here. The rule says to do all that. Yeah, doesn't look so pleasant. Well, maybe I'll make this as an exercise for homework due Thursday. I'll leave it to you to check that these first two terms in our situation at least are 0. These first two terms. I think I'm officially making that a homework problem right now. This abstract setting for our problem, our situation, I want you to check that these first two terms are 0. And so we're left with just this thing over here. This Leibniz's integral rule says the answer is going to be the integral from 0 to W, because for us, the A of X is really an A of W, which is 0, and the B of X is really a B of W, which is just W, times the derivative with respect to not X, but W of this thing. It's a partial derivative symbol because there's two variables in here, an X and a W. However, the W only appears in the second factor there. This first factor is a constant with respect to W. Differentiated with respect to W, it stays as is. So we really just end up differentiating capital F. And that, of course, is little f. And that thing right there, that's the convolution formula in this situation. It is the PDF of capital W. And I could also write it as F sub X star F sub Y of W. And again, in this spot right here, we use the Leibniz integral rule. Okay. I'm not going to prove the Leibniz integral rule. Okay, that's beyond the scope of what we're doing here. We're just using it. And again, I'll leave it as an exercise due Thursday. I'll put it on Moodle to confirm that in our situation, these first two terms are 0. Question?
Does it not matter that it's a little f in the Leibniz integral rule if we're using it as a big F at first?
The little f down here in the Leibniz integral rule, up in our situation, that's really represented by the product of little f sub x and capital F sub y. Is the product of those two things is what the little f down here is. So the notation is, not the same, but it's the idea that's important. What is the function you're integrating? That's the key. Okay, so Leibniz integral rule, you probably never heard of that before this point. I think I learned about it in my multivariable calculus class, but I've never taught it when I've taught multivariable calculus. And before Jed Yang started teaching it, I've taught multivariable calculus plenty of times, but I've never taught it because it's not really commonly used. Here's the main situation where I know it's used. Okay. This convolution formula is a good thing. It does make calculations simpler. Let's go back to our example before spring break, where we're looking at the sum of two exponential random variables that were also independent. So X and Y are going to be exponential with parameter beta. And remember, beta is the mean of that exponential. And they're going to be independent. Question is, what is the distribution of x plus y? What we saw before spring break is that this turns out to be gamma parameters alpha and beta, where alpha was 2. Remember that? We derived that before spring break in 2 ways. One with moment generating functions and the fingerprint theorem, which is the easier way to do it, and one with a double integral, which was the harder way to do it. And I got them in the Mathematica notebooks, the details, and I'll briefly show them to you, but we're not going to actually go through it. Confirming this with convolution formula is another way to do it. And it's easier than the double integral method, though I'm not sure if it's easier than the, not necessarily easier than the moment generating function method. So how to do that? Do that. Confirm with convolution formula is what we're trying to do here. And by the way, of course, exponential random variables are non-negative. So we can use this formula. I can use the convolution symbol, the star symbol, if I like. And the formula from the previous page is that I do the integral from 0 to w of little f sub x evaluated at x times little f sub y evaluated not at x or y, but instead at w minus x. Integrate with respect to x. And this turns out to be an easy integral to do. What's the PDF of x? It would be 1 over beta e to the negative x over beta, right? There's an exponential PDF with parameter beta if I call the variable x. PDF of y, if the variable was called y, would be 1 over beta e to the negative y over beta. It's the same PDF, really, just a different variable name. But I'm replacing y with w minus x here. That's an x there. Can't quite see that. That's an x. Of course, I can distribute the minus sign through. That's the same as e to the negative, e to the positive x minus w over beta. And I could write that using properties of exponents like this. And then continuing to use properties of exponents, if I combine these two things, I get e to the 0, which is 1. So I'm really integrating 1 over beta squared. There's 2 factors of 1 over beta. E to the negative w over beta dx, not dw. This is a constant with respect to x. Very easy integral to do. Get 1 over beta squared e to the negative w over beta times x. X goes from 0 to w. And when you simplify that, that's 1 over beta squared. Replace x with w. I'll put it in the front. W e to the negative w over beta. And that is the PDF of a gamma. PDF of gamma when alpha is 2 and beta is beta. All this is assuming w is greater than or equal to 0. That is definitely easier to do than the double integral method, where we did a double integral to find the CD. There was the CDF method computed with a double integral. We did the double integral. Then we had to differentiate the double integral to get the final answer. I'll show you the details, though I won't go through them step by step. This is quicker using the convolution formula, but you gotta know the convolution formula. Ready for me to show you the details? Again, we're not going to go through them step by step. So here, okay, I've got a number of things in this notebook. And again, I'll share this notebook. Somebody could remind me to share the notebook because I often forget. So here's the derivation I just did with the convolution formula. With moment generating functions, the computational details in Mathematica are here. I'm not going to enter this code. Here was the double integral method. This is what we did before spring break. Did that double integral. Got this for the CDF. Then we differentiated to find the PDF. Got the same answer. Okay, so once you've got the convolution formula, it is easier. So I'm probably going to assign another homework problem where you're going to use the convolution formula. It's a second homework problem to do in a different situation. Can I clarify anything? Not saying this is easy to understand. Just trying to make use of it. And it is good to see the CDF method coming into play again. We are trusting this Leibniz integral rule to get this answer. Convolution is a useful thing. All right, what should we do next? I would like to use Mathematica for a fair amount here. So my next goal is to do one more problem. This is the final problem we'll do. I'll probably give you a homework problem similar to this, where we're going to add two random variables. But this time we're going to make it harder on ourselves. Wait, isn't this already hard enough? We're going to make it harder on ourselves by making these random variables not independent. So we will not be able to use the convolution formula. We'll have to do a double integral. And we'll not be able to use independence to simplify that double integral. We'll just have to do it as it is. Okay. This will bring up a question, when would you use a situation with non-independent random variables? I'll maybe talk about that a little bit on Thursday. Before we do that, maybe we should look at using Mathematica to confirm things here, because we're going to use Mathematica further on down, so it might be good to review that. So here I was using Mathematica in various ways. For example, to remind myself of the PDF of an exponential. That's code that will tell you what the PDF of an exponential is right there. PDF exponential distribution. Do note that in Mathematica, you have to plug in 1/beta as the parameter instead of beta itself. 1/beta is often called lambda, and it's related to Poisson random variables. I don't know if you remember, Poissons and exponentials are related. I have talked about that. If the Poisson is like the count of cars that come into an intersection during an hour, if the parameter is lambda for the average number of cars that come in an hour, 1/lambda is the beta for an exponential that gives you the wait time between cars coming into the intersection. If that went over your head, don't worry about it, but that's something to keep in mind. Just reminding you, you can use random variate to generate data. So this is going to generate data from two exponential distributions. And if I do it separately like this, X data and then Y data, effectively they are independent simulation wise. The results of one of these is not going to be affected by the results of the other. I've entered them. What's the X data? I could do this and see them all 10,000 numbers. 10,000 numbers there. Of course, the semicolon will suppress outputs, so I don't have to see the numbers. Mean of an exponential distribution is beta. In this case, 1 over beta is 0.1, so beta is 10. We should expect a mean of 10, close to 10 for both the x data and y data. Standard deviation for exponentials also equal beta. Variance is beta squared. So these numbers are all close to 10. Not exactly 10 because of simulation. You can make histograms, and you can see by if you plot the PDFs of these things, well, not the PDFs themselves exactly, but scaled up versions, 20,000 times the PDF. You can see, especially with 10,000 data points, we got a pretty good match. W data, that's where I'm adding the x data and the y data. W is x plus y. I'm not doing that with random varied, but I'm doing it with table because I'm wanting to take the actual x data and y data that I got, although because I use colon equals, it'll probably redo it, and compute W data for the sum. It takes a little longer. And here I computed the mean and standard deviation. Notice 20. Hey, 10 plus 10. The mean of x and the mean of y are both 10. 10 plus 10 is 20. That's very close to 20. 14.2, what's that close to? How about square root of 200? Is what it's close to. 100 plus 100. Remember, the variance is 10 squared is 100. And if you make a histogram and plot also, notice this is 20,000 times the PDF of W. Notice the extra factor of W in there. That's a gamma with alpha equal to 2. It's not an exponential distribution, but it does follow, the simulated data does follow the shape of the PDF for a gamma distribution with alpha equal to 2 and beta equal to 10. The 0.01 here, by the way, is 1 over beta squared, which is part of the formula that we did get. 1 over beta squared. So it's nice to see those all working together. I think I'll skip all this stuff. Let's jump on to the 2 non-independent random variables example. Sum of 2 non-independent random variables. How do you handle that kind of thing? Okay, well, we're going to do an artificial example, no applications here. I hope I can think of an application for Thursday's class, though we probably won't go through the calculation details. There's a joint density for a bivariate random variable, a random vector, if you will, random point. They have joint densities. This is going back to chapter 5 again. You should not assume, in fact, if you're just sort of writing down some sort of joint density or at random, in all likelihood, the variables will not be independent. Because what's the definition of independence? It's that the joint density has to be the product of the marginal densities. In all likelihood, it will not be. Can we confirm that? Mm-hmm. Let's definitely have Mathematica help us with lots of calculations now. But you're going to need to pay attention to the key ideas, and I will write some things down as we go to remind you. So here I went ahead and put this function into Mathematica, and I went ahead and put it in as a piecewise function. One thing that would be good to do here is to draw this domain. The domain where the joint PDF is non-negative, is strictly positive, I should say, is when x is between 0 and 2 and y is between 0 and not a constant, but a function of x. A linear function of x with a negative slope. This domain is going to be a triangle. Let's draw it. So x goes between 0 and 2, and y goes between 0 and, it was 1 minus x over 2. You will want to make drawings here with me. in your notes. One minus x over 2 has a graph that is a straight line with a y-intercept of 1 and a slope of -1/2. Its x-intercept is 2. There's our triangle. That line has this equation. These inequalities mean we're inside this triangle. That is the domain in the xy plane where the joint PDF of this bivariate random variable is strictly positive. It's 0 elsewhere. Again, I did put it into Mathematica as a piecewise function just to see if it would work. The double ampersand here is to say I want both of these conditions to be true. Effectively, this is like an and. You put true here for the otherwise, that's just Mathematica's convention. And here I did want to confirm that the double integral of this entire thing over the entire plane, in fact, does integrate to 1. It is keeping track of the fact that it's 0 elsewhere. Takes a while to compute, but it does confirm it to be 1. But I also could do the double integral, not from -infinity to infinity, but over the triangle itself, and it also confirms to equal 1. Okay, you want to write this PDF down if you haven't yet. It's going to be our example here. What am I about to do? I'm going to try to figure out once again the distribution of the sum x plus y. That's my goal. And I also want to confirm that it seems correct with simulations and that kind of thing. That's big picture where we're going here. Because the variables are non-independent, the CDF method still works, but it's just harder, you might say. Yeah, it is harder. We're not going to be able to use the convolution formula because that only works when the variables are independent. We're not going to be able to use the fact that the joint density is the product of the marginal densities because it's not true. First thing we should do is confirm that the joint density is truly not the product of the marginal densities. How do we do that? Let's find the marginal densities. What's the marginal density of X, for example? That is in the book, the definition of the marginal density. You need to integrate the joint density with respect to Y. You need to get rid of the Y, so to speak. What's the domain of the integral? It would be the values of Y that Y varies over for any given fixed value of X. Now I could go ahead and put all Y here. I could put a -infinity to infinity, and that doesn't hurt. I will go ahead and put a -infinity to infinity at the start. It doesn't hurt to put that. It's still true. However, for purposes of computation for this example, I want to imagine when doing this integral that X is fixed. And just like before, when I'm looking at the triangular region and imagining X to be fixed, Y varies between the second coordinates of these points from 0 up to the second coordinate at that point, which depends on X. It's 1 minus X over 2. So this integral ends up being 0 to 1 minus X over 2. I'm integrating out the Y. What's left does depend on X. What does it equal? It's down here further. Where did I put it? Okay, it's this thing right here. Equals that. That's the marginal density of X. Let me go ahead and write it on the paper. I'll write it with the X squared term first. -5/8 X squared plus 7/6 X plus 1/6. What's the domain where this is valid? It's valid when X goes between 0 and 2. Right, in the triangle, X goes from 0 to 2. You might want to confirm that it is truly a PDF. We will do that. Just give us a minute here. How about the marginal density of Y? I do the analogous thing. I integrate the joint PDF with respect to X. If I want to simplify that domain to some finite domain, then I need to look up at my picture and think of Y as fixed, not X. And say X varies from the first coordinate of this point to the first coordinate of that point, not the second coordinates. 0 is the first coordinate. What's the first coordinate of that point right there? It depends on Y, not X. Take this equation and solve for X. X over 2 is 1 minus Y. X is 2 minus 2Y. That's the upper limit of the integral, 2 minus 2Y. Again, we'll have Mathematica do the details. What do you end up getting? Which I did them both here. You get this thing, 2y squared minus 14/3 y plus 8/3. 2y squared plus 14/3 y. Was it minus 8/3? Minus 14/3. Minus 14/3 plus 8/3. Yep, okay. I suppose part of your homework, I could just ask you to confirm this kind of stuff by hand too. I'm not exactly sure what the homework's going to be yet. This is a y going between 0 and 1. Think about the picture. Are these really PDFs? And can I visualize all these things in any nice ways? Yeah. Actually, let's go back up to the joint PDF. Here's another way to confirm that the joint PDF integrates to 1. Notice the difference between this double integral and this double integral. In this one, y is done first and then x. X goes from 0 to 2. Y goes from 0 to 1 minus x over 2. That's the way we've usually done it. But in this one, x is integrated with respect to first and then y. I switched around the dy and the dx. I therefore have to change the limits of integration appropriately. Y that goes from 0 to 1. Look at the picture. Y goes from 0 to 1. And for any fixed y between 0 and 1, for the inner integral, x goes from 0 up to, there it is, 2 minus 2y. This should integrate to 1 as well. And it does. This can be interpreted geometrically. This graph, this red graph, is the graph of the joint PDF. Instead of the area under the graph being 1, it's the volume under the graph that equals 1. So the volume of the region under this triangular kind of graph here is 1. Ignore this thing over here, that's numerical error. It's not part of the graph. That volume of that solid would be 1. Can also interpret this in terms of what's called a contour map. This is the triangle where the joint PDF is positive, and you see level curves, which are straight lines because the joint PDF is a linear function. And I don't know if you can see those numbers, kind of small, but they keep getting bigger as I move to the right, which the graph keeps getting higher. The outputs of the joint PDF keep getting higher. What's the intuition beyond what this is modeling? This is modeling two-dimensional data, XY data, where X and Y have to vary over a triangle like this, and where the joint PDF is higher in value, the data is denser. We're going to ultimately see that by the end of the class here when I do a simulation. We're going to see denser data over here because that's where the joint PDF is higher in value, and less dense over here where the joint PDF is lower in value. Yeah, here are the marginal PDFs. Let's confirm these integrate to 1. Yep. So this first one, I'm integrating the marginal PDF of X from 0 to 2, and this one I'm integrating the marginal PDF of Y from 0 to 1. I get 1 in both cases because I have to. There's the marginal PDF of X. There's the marginal PDF of Y. X, it's interesting. X has kind of a close to symmetric distribution between 0 and 2. And the data for X would be densest near 1. Y is kind of like an exponential decay. It's not an exponential decay, it's a quadratic, but similar in nature, right skewed distribution. The data for Y would be densest near 0. You might wonder if is that inconsistent with what we're seeing up there? That's maybe a little unclear. I think it is, with Y being denser near 0 is corresponding to the fact that these points have a Y coordinate near 0. Yeah, it's making sense. Here's something new. I've never shown this to you before. You can use a built-in command called probability distribution to create user-defined probability distributions, PDFs and CDFs. That's the marginal density of X. This is the marginal density of Y over the appropriate domains. This code doesn't really do anything seemingly when I enter it, but it did, and it stored some information in its Mathematicus memory. By the way, you might be wondering, where did I get this curvy D? If you do escape, SCD, escape, it makes a cursive D. SC, escape, SC, escape. You can just copy and paste it if you want. Seemingly it didn't do anything, but it did. If I now combine random variate with one of these things, that will simulate sampling from this distribution. So for X, this in all likelihood is going to be a number near 1. Most of the time. Most of the time it's relatively close to 1 because X has a distribution whose mode is near 1. If I do it for Y, Y is right skewed, denser values near 0. In all likelihood, this is going to be a number closer to 0 than it is to 1 most of the time. I've never shown you that before. Probability distribution done in this way, combined with random variable, will simulate from these kinds of distributions, and I can do more than one sample. And here I'm doing 10,000 samples of size 1,000 and then making histograms as well. Hey, yeah, kind of looks like the shapes of those PDFs. What's the means? The mean of X is 17/18. I can that's confirmed with an integral. I can also confirm 17/18 with that simulated distribution. 17/18 there again. This is the standard deviation of X. Here's the mean of Y, 5/18, and its standard deviation, and those approximate to these numbers. Okay, now what am I after? Remember, so that's just all set up. Joint distribution of a bivariate random variable X and Y. Compute the marginal densities. Simulate the marginal densities if I like. But now the key, I'm after the key thing here. W is X plus Y. What's the distribution of W? Although I forgot to mention, it's definitely not, they're definitely not independent. Okay, these marginal distributions, if you multiply these things, you definitely do not get the joint PDF. The joint PDF is linear, whereas these marginal PDFs are quadratic, for one thing. That's true, so they're not independent. So again, I can't use convolution, I can't use independence in any way because they're not independent. But I can still use the CDF method. And I can still compute it ultimately by doing double integrals. The details are unpleasant, but doable. We have to split it into two cases, though. That's an extra complication. Case 1, W is between 0 and 1. Case 2, W is between 1 and 2. Why? Why do I have to do two cases? Let's look at the picture again. Let me, in fact, redraw this. W is between 0 and 1. Here's the domain where the joint PDF is positive. However, the domain of integration to figure out the CDF of W is not the entire triangle. The CDF of W is where X plus Y is less than or equal to W. That's completely analogous to the other examples from today and before spring break. The triangle to integrate over is one like this, just like earlier today. If W is between 0 and 1. So I'm not integrating over the entire domain where the joint PDF is positive. I'm integrating over a smaller domain, a different triangle. And that line right there still is the same equation as before, Y equals W minus X. Because I'm thinking about where is X plus Y less than or equal to W. Equivalently, where is a capital Y less than or equal to W minus X? I'm using capital letters up there because I'm thinking of them as random variables, and here I'm using lowercase. Not a big deal. So integrate over that triangle is what we're doing here with case 1. So the limits of integration are what you see here. X is my outer integral. It goes from 0 to W. W, think of W as fixed. Some fixed number between 0 and 1. For any fixed value of X between 0 and W, Y goes from the second coordinate of this point to the second coordinate of that point, 0 to W minus X. That's the limits of integration for the inner integral. Of the joint PDF, which is this, and I cannot factor that as the product of the marginal PDFs. If I do, I'd get the wrong answer. But that's actually better here because the product of the marginal PDFs would be more complicated because they were quadratics. So it does actually make it easier to not do that here. Do the inner integral with respect to Y. So I need to integrate 4/3 X plus 1/3 Y with respect to Y first. I'll get 4/3 XY, because 4/3 X is like a constant, plus 1/6 Y squared. Right? Integrate 1/3 Y, get 1/6 Y squared. Y goes from 0 to W minus X. So when you plug in 0, you get 0. When you plug in W minus X, you get this. And then you'd have to simplify that. It's, a little unpleasant, but you could do it in about a minute or so and get this. And then integrate that from 0 to W. And here's the final answer in simplified form. It's fairly simple. When W is between 0 and 1. W is between 1 and 2, it's not so simple. We'll come to that. Here I did had Mathematica confirm calculations for me. Like expanding this thing here to get this thing. And confirming the integral does give you, in the end, 5/18 W cubed. So case one, it's not terrible. Case two, when W is between 1 and 2, I definitely would not want to do without technology. I mean, I could, but it's just like, it would be a real big pain. Why? Because the picture for case two gets more complicated. That's why. This green triangle shifts upward, so to speak, gets bigger, and the region to integrate over gets more complicated. It's no longer a triangle. What is it? Another drawing. I'm not doing this very well. If W is bigger than 1, if it's a little bit bigger than 1, what does the new triangle look like? Well, the triangle where x plus y is less than or equal to W looks like this. That's W there. This is still W here. But that triangle is not the domain of integration. Well, you could call it the domain of integration. However, the joint PDF is 0 up there because you'd be outside of the black triangle. So to actually do the calculation, you effectively have to think about integrating over this region here, which is no longer a triangle. Though you can think of it as a trapezoid and a triangle combined. So the point is you have to integrate over this trapezoid and then add the integral over this triangle, which does complicate things, and in particular complicates things in the sense that you got to figure out what the coordinates of that point are in terms of W. The black line has equation y equals 1 minus x over 2. The red line has equation y equals W minus x. To figure out where those intersect, you got to set them equal to each other and solve for x. So W minus x equals 1 minus x over 2. I could subtract 1 from both sides and add x to both sides, and then I could multiply both sides by 2. X is 2W minus 2. That's the x coordinate of the point of intersection. That point is 2W minus 2. Does that make sense? And that will be less than W when W is less than 2, which it is. And the y coordinate I could figure out by plugging this thing into, for example, there. The y coordinate would be W minus x, which is W minus this thing. And that'll be 2 minus W when you simplify it. Actually, we don't really need the y coordinate, but I can find it anyway. In the end, what happens is you have to do the sum of two integrals, these two integrals. And doing those would be a pain. Very easy to make a mistake. If I had to do it, yeah, I could do it. I don't know, it might take me 10 minutes, something like that, I guess. Notice with the first one, x is going from 0 to 2 minus 2W minus 2. And y goes from 0 to 1 minus x over 2, which is the black line. And for the second one, x goes from 2W minus 2 up to 2. No, excuse me, up to W. I'm integrating over this triangle here. And y goes from 0 up to W minus x, which is the equation of the red line. And Mathematica says that's the answer. So altogether, W has, the CDF of W has a piecewise formula. And there it is in all its glory. Somebody can remind me after class to share this with you. Put it on Moodle. You might wonder, and you might hope, is this continuous? Shouldn't it be continuous? These pieces have to match up at 0, 1, and 2. And they do. You can plug in numbers to confirm they match up. Or you can just graph it. It's a continuous function. Its derivative is the PDF. Technically speaking, it's not differentiable at 0, 1, or 2. There's corners in the graph, I think. Well, actually, it would be differentiable at 0. Probably not at 1 and 2, though. There's like corners. There's a corner in the graph for sure here. Maybe it kind of at 1, it looks like maybe it's smooth there. Hard to say for sure. I just differentiated the pieces and didn't worry about the endpoint. So if you differentiate this thing with respect to W, bring down the 3, 15/18 is the same as 5/6 W squared. 5/6 W squared. Differentiate this one, you'll get negative 11/6 W squared plus 14/3 W minus 2, it looks like. Yep. This can be put in. This turns out to be continuous as well, though it didn't have to be. So I guess it does mean it's differentiable at 0, 1, and 2. I wasn't necessarily expecting it to be continuous. It does integrate to 1. What's its mean? It turns out to be 11/9, which is approximately 1.2. What's its standard deviation? Turns out to be about 0.37. Remember my goal. Now, okay, part of the goal has been met. I'm saying there's the PDF of W. I did double check it. In fact, this example was from a different book, and that was their answer too. So this is right. What I'd like to do now to finish class is try to confirm this simulation-wise. Like, again, this is the main theme, confirm theory with simulation if you're feeling uncertain about the theory, which, you know, you very well may be. I wanted to confirm it with simulation. So I can do the probability distribution thing that I already showed you. I can make a histogram and plot it with the PDF and see that I got a good match. That's some confirmation. That's the PDF of W multiplied by 1,000 to make it scaled up. Matching the simulation, that's good. That's actually not really confirming that I haven't made a mistake though, because I'm just using my answer in both spots. There and there. The mean should be close to, what was it? 1.2, and the standard deviation should be close to 0.37. That's simulated data there. But here's the kicker. Can we do a simulation to confirm it's truly matching the behavior of the sum x plus y? Low on time here. Have to do a quick explanation. To get Mathematica, I was hoping I could avoid this in Mathematica, but it seemed that I couldn't avoid it. To get Mathematica to confirm this, I had to actually compute the conditional densities, or one conditional density at least, which we haven't talked about all semester. It's in chapter 5. It was in Prob and Stats. It's related to curves of regression. And in fact, I'm going to show you a curve of regression here. The density of the random variable y given x equals x. In other words, if you know what value x takes on, what's the behavior of y? That's the definition of the conditional density. It equals this in this example, it turns out. When you look at this expression, you want to think of x as fixed and y as the variable. And if x is fixed, then that's a fixed right endpoint as well. This does integrate to 1, though it doesn't look like it will at first. When you integrate it at first without doing a simplify, it gives you this answer, which you're like, oh, that didn't integrate to 1. But if you simplify it, that's actually a big, crazy 1. The area under this graph is 1 no matter what x is, but the domain does change and the graph itself does change. Those are the conditional densities for different values of x. What's the curve of regression? It's the mean of those densities. I'm integrating with respect to y times this conditional density. This thing depends on x, and you can't get rid of the x there. If you plot that function of x, you get this pretty picture showing you that for different values of x, I can approximate the mean of the corresponding value of y by this curve. This is the curve of regression. For example, when x is 1, I should expect the mean value of y to be close to 0.3. But how do you simulate that? That's all this stuff, and I'm not going to take time to explain it. But there we have simulated data for the joint distribution, matching the density, the joint densities being more dense down here and less dense over here. And this is finally where I'm taking that simulated data and adding the x and y coordinates essentially. And this is the final confirmation. This is close to 1.2 and this is close to 0.37. Without getting into details of fully explaining everything. So yeah, I'm not exactly sure what form your homework's going to take, but I will put this on Moodle. Somebody again remind me. And even though that was difficult, I hope it still felt rewarding to see everything come together.